All right, so today I am pleased to introduce Cassie Lumbrazo for her PhD defense. And Hannah gave me the brilliant idea that you should start an introduction by saying the first email you ever received from the person. And that's and so I looked, and the very first email exchange Cassie and I ever had, I said, "Can you come to graduate visitation on this date?" And Cassie said, "Yes." That was all it said. But it wasn't any like secret revealing. So I didn't know what I was getting because all she said was yes, but that was a good thing because it meant that we had a lot of years together. Cassie graduated from Clarkson University in May 2018 with a dual major in math and statistics and civil and environmental engineering. She was going for the majors with like the most words. And she graduated with a service award for doing service there and carried it on here. I don't think we ever gave her a service award, but if we did, she would have earned one. And so she came and over time, she started following a tree project. And the tree project goes back to Susan and I back in 2013, wrote a paper that we called Trees of the World. And Cassie took this very personally, and then she decided to study trees all over the world. So in 2020, she went to Grand Mesa, Colorado, and studied all the trees there. In 2021, she went to Davos, Switzerland, and studied all the trees there. In 2022, she went to Norway and Finland and checked out all the trees there. And she did not go to South America because actually they don't have a whole lot of trees where there's snow, and so it wasn't worth her time, but she might just go there on holiday to look at
That's next for fun, man.
In terms of what she's accomplished during the time, you know, first, like she was right smack dab in the very middle of COVID, which like was hard for all of us. And I think there was a quote I had on my door during that time that said, like, courage doesn't always roar. Sometimes courage is the small voice that tells you I'm going to try again tomorrow. And I think like, that was a lot of how we all felt during that time. And like Cassie kept getting up no matter what happened, like she kept going. And so she got a grant from NCOM to fly that you'll hear about. This was a LiDAR. She wrote the grant, she got it funded. It was COVID, wasn't going to get funded. She managed to negotiate through COVID, got it flown in 2021, was a 2020 grant, it got going. She also managed to get a repeat flight with Mary Rapid, she's going to talk to you about. That was also her own grant application. The other thing that she's really spectacular about is reaching out to people. When she came into the group, Cassie said, "Well, so what do you do for outreach?" And I'm like, "Well, I don't know, this website." She said, "Well, we could fix that." So she created a Twitter account back when Twitter was cool. Yeah. And she created, and we went from like, what, we started like 10 followers and we got like, I don't know, 800 or something.
Yeah, we're up there.
She took over a project in Zooniverse that actually like artists just did like 10 years ago and expanded that to, I don't know, it's like 12, 13,000 followers on Zooniverse now. She also made it much broader with trees all over the world. For all spots she visited, she got on there. She mentored at least 3 undergraduates. I may have missed some in doing the Zooniverse. She mentored them through COVID, through a lot of like strife and pain and keeping them going where everything was online. She also won the best student presentation at AGU. Out of 28,000 attendees, I think more than one got that, but still out of 28,000, it was pretty distinctive. And I can't even read things because my eyes are going, but the other interesting thing you might not know if you read her CV is she started Watercolor Wednesdays during the pandemic where people could post watercolor paintings. And she's a very good watercolor artist. And I don't know if you still post on Wednesdays, but
yeah,
that was really fun to keep me going. Post the watercolor on this Wednesday. So with that, I'll let her tell you about her science. Wow.
That was like such a great introduction, and my mom and I are about to cry, so everybody relax. Wow, Jessica, thank you so much. Yeah, I've been working with Jessica for a few years, and we've had a great time, highs, lows, many highs, and I'm going to tell you guys about some of them today. So let's see if this works. Okay, excellent. And also the energy in this room is excellent. You got it? No, it's okay. The energy in this room is excellent. This just shows me how excellent of a community I have in my life, so thanks, everybody. Okay, so I want to start by, I'm going to start this, so. I want to start by just recognizing my committee. So Jessica, my advisor, who has been just helping me through these past few years, Brian Harvey, my GSR, taught a forestry class that actually just like kept me in this forest snow world. Brittany Johnson, thank you so much for joining our committee and contributing to our soil moisture conversations later. Susan and Emily, you two have been excellent mentors, and I'm just so grateful to have so many powerful women in my life to pull me through this. So I'm excited for our conversations later, and we are gonna get into it. So, all right, this is kind of just a presentation outline. I'm gonna do this a little differently. A lot of times people in their defenses go like chapter 1, 2, 3, and keep everything kind of consecutive, but I'm gonna give some background on forest snow processes, tell you guys a little bit about my first 2 chapters, pretty brief, and then I'm gonna jump into this forest management work in Washington State, which we're all very excited about. Susan, Emily, Jessica have all been working on this a while, and we finally just have the like meat of the results for this work. So I'm gonna just be privileged enough to be able to present that work to you guys today. And yeah, that's the end of the presentation. It's gonna be a majority of it will be the analysis of that project, and yeah, basically trying to figure out how forest management impacts our snowpack in Washington State and our water availability. Well, I had to start with snow and trees. So, you know, a lot of people here and online know that snow is important, but snow matters for water resources a lot of places, and a lot of those places overlap with trees. So if I don't need to tell you, this spreads over the world. Jessica gave you a beautiful introduction of my previous very fun times looking at trees of the world. And when you're out in the forest, it looks something like this. I took this photo in Switzerland. And the experience you can have can be being out there and seeing that trees can interact with snow on the ground in a lot of ways. If you're out in a meadow, it would look very different. You would just have, you know, snow accumulating, maybe smoothing over a landscape. But when you have trees involved, it complicates the processes a little bit more. And that's been the first 2 chapters of my work really dove into that, and we expanded on that in the last. So what do you see in that video? You really see a few things. You see snow interception. So you actually see snow falling, intercepting onto the canopy. And then you see some other processes on the ground happening. If you have short wave radiation, solar radiation coming in, you could have trees shading the snow on the ground and impacting the snow on the ground as well. And also trees get really hot. And when they're outside and getting exposed to solar radiation, this is a map from Ty Webster, one of my mentors as well. And this is just showing the temperature of the tree. It's hot. And what happens is the trees essentially warm up and they emit long wave radiation, and they can melt the snow around as well. So all these processes are often happening at the same time. And they can pull, it's one of these processes that it can pull snow storage in different directions. And there's a lot of things where we know for certain how they impact snow, and trees can kind of go either way. And so my PhD has been looking at this. The title of my PhD was Combining Multiple Observations to Improve Our Understanding of Forest Interactions and Inform Management. My introduction chapter and my chapter 1 are in here. Where we're using observations of snow interception and unloading in different climates to inform models. So that's really the focus of those projects. And in the last projects, we are using all of those processes now, not just looking at interception, but we're looking at all these processes to see how they can inform forest management. So it's a different application, so this work looks at similar processes, but we're kind of focused on different goals here. And this is the horrendogram of my accomplishments. So the introduction chapter is, this is published, and I'll briefly go over that. There was a follow-up chapter with that, working with my international collaborators. And after that, we're moving into forest management work, which was essentially in the past year and a half. So we will start here. And we're talking about canopy snow interception, right? Just this one piece of the larger processes that are happening. And what can happen is you have interception, the snow can melt and actually unload to the snowpack on the ground, but it can also just melt off and contribute to the snowpack below. It can sublimate back to the atmosphere. You can just lose all of that moisture to the atmosphere. So all these processes just in the interception component are happening at the same time. And I love to point this out, even though I didn't actually study this, is that this is a ponderosa pine. And I really do think, the forest structure matters, right? We know this, but we don't necessarily directly look at this. But yeah, so the type of tree that you have could also impact these things. We try to use metrics to be able to look at these things. But yeah, I think that these conversations are very important when you're talking about interception. So this first paper, Jessica nicely touched on this, but we we basically observed snow interception by using time-lapse photography, and this paper is published. This was part of the citizen science project with a lot of volunteers. It was really, really fun work to mentor undergrads with this work as well. Essentially, we found that we use these observations to evaluate the performance of models, and we found that the models were not transferable across climates and they required local calibration. This is the short story. I'd love to talk to you more if anybody has any questions. And this motivated the first chapter of my PhD, which is essentially trying to determine meteorological variable thresholds for snow unloading across climates. So we just built on that other chapter to say, okay, in previous work, if our models are not transferable, what do we have to do to make them transferable? So we should look at unloading in different climates. We did that. Jessica mentioned I traveled, I got to see some places, look at stone trees, and look at a lot of time-lapse images. So we expanded to Sodankylä in Finland and Davos-Lorette in Switzerland, and we have a site here in the United States in Colorado. I'm also not going to get a chance to talk a lot about this work, but we tried to cover a range of different meteorological variables, and we found that snow unloading and snow staying in the canopy from observations, and we were essentially able to statistically determine thresholds in the meteorological variables that determine unloading in these different climates. So, like I said, I'd love to talk to you guys more about this work, but the summary is that we found that the threshold for wind-dependent unloading is lower in Arctic climates and compared to mid-latitude climates. So it's just really cold. The snow is typically cold and it can blow out of the trees a lot easier. And the threshold for temperature-dependent unloading is higher in mid-latitude climates compared to the Arctic. So you can actually have the temperature threshold, you really have to increase that to get snow out of the canopy in middle latitudes. Okay, so that is we took a ton of observations from time-lapse photography. We put them together, we looked at meteorological variables, and we tried to inform models to better predict canopy interception and unloading. And now we are going to move into this forest management piece of the project, which encompasses my chapters 2 and 3. So in those first part, we were kind of globally looking at all these processes, but now we're going to hone into Washington State for this work and focus in on these processes here. So like I said, this is chapters 2 and 3. So if we're talking about forest management in Washington State, then we have to talk about wildfires because we are managing our forests often for wildfire resilience. And what we're doing is, there can be certain things that we're doing, such as controlled burns or logging to be managing for wildfires. And the point is that we want to create fire resilient forests. We want to create forests that can withstand, can reduce the high severity crown fires and withstand any climate impacts that can come related to wildfires in this region. It's not the only reason though we're managing forests. I just want to highlight we're managing them for a lot of reasons. And they can be to have healthy forests, have wildlife habitat. It's also a monetary component of just sustainable logging, and recreation in forests if you like being outside in the forest like me. And then this water resources aspect, which is where we sit as hydrologists. So we really want to ensure that there's appropriate stream flow for fish and have it at the correct time of year and ensure that there's water downstream. So when we're managing for water resources and fire resiliency, we're also thinking about all these things. I'm focusing on fire resiliency and water resources in this talk, but I want to just recognize that management is not just in those 2 locations. So if we're managing for water resources, then we're managing for snow. In the Western US, we get all of our water comes from our snowpack, and this is snow depth over time, and then that's stream flow in blue. So our snow depth eventually becomes stream flow, and there's a lot of complicated things in there. But if we are managing our forests in the snowpack areas, we need to know what's going on. So in a climate change world, there's a lot of processes going on. But if the temperature is changing, a lot of studies have shown our snow accumulation may be less, it may change, but there's often just earlier snow melt. And that's just something we're scientists sitting here talking about forest management, and we're not gonna necessarily solve climate change with this problem, but our goal is to make sure that when we're changing our forest structure, this delta forest structure, we wanna make sure that we're not pushing climate change we're not pushing into the same direction as climate change, right? We want to create forest management practices that are creating a buffer against climate change. And it would be really great if we could even push it a little bit further and actually extend our snowpack using changes in forest structure to extend our snowpack, even if that's just a few weeks. It could have pretty large implications for stream flow and for fish at certain times of the year. So yeah, how does changing the forest structure during management impact our snowpack? This seems like a pretty simple question, but it actually depends on climate. So if you change the forest structure, then in different regions, different things happen. Snow lasts longer in open areas versus under the forest, and this strongly depends on temperature. So in warm winters, long wave radiation dominates, which is one of the processes I previously showed you, and trees end up melting, trees melt with snow. So snow is gonna last longer in the open. And in regions with cold winters, shortwave radiation dominates one of those processes, and trees actually end up providing a lot of shade to the snow, and snow is going to last longer in the forest. And this is dependent on this DJF, which is the December, January, February winter temperatures. And so this winter temperatures really matter, but there weren't a lot of observations. The observations were primarily in really cold or really warm regions. And of course, in Washington State, we have all of these. We have a very large spectrum. If you've ever driven across Washington State, you can go from very warm areas to like feeling like you're in the Arctic and the high latitude to the desert. And actually, there's a region of Washington State which is in a climate transition zone. So it's actually between these extremes where the temperature is kind of hovering around -1 degree C. And there are many hypotheses. A lot of people, I'm not the first person to be looking at this. This has been years of work. There's hypotheses for what direction the forest structure pushes snow depth in these regions, but there wasn't a lot of observations and direct studies of the forest structure and snowpack in this climate transition zone. So for the first time, we can test these hypotheses. So like I said, I'm just privileged enough to be able to share these results. It's a lot of people's work, and I'm gonna highlight some people's work here. We're in Washington State. These are some outlines of our beautiful watersheds here. And one of them is the Yakima River Basin. So I'm gonna talk to you about some forest management going on here and what we're studying. But first, I wanna just highlight that we have fish coming up. We have fish that migrate all the way up from the ocean and go all the way back in the spring. And there's very long distances they need to travel, and the stream flow is really important for them in these regions. This is a forest cover map. So the Yakima River Basin is not entirely forested, but the green areas are the forested regions, and they're the higher elevation areas. The lower elevation areas are actually all agriculture regions. And so this is a pretty arid climate. There's the divide of the state, that line that goes through the Cascade Range. And so it's all the forest structure in the higher elevations that have also seasonal snowpack, and that also have wildfires. Often there's wildfires. So this is historical wildfire areas of the region. So a lot of our historical wildfires are on the east side. So forest management is actively happening in these areas. And it's really important that we are changing the forest structure to protect against wildfires, but we need to make sure that we're protecting for water resources as well. Let's zoom into our field site. So we are talking about an experimental forest on Clay Elm Ridge. This is what it looks like. This is a photo from Mark Stone, beautiful drone photography. And there's forest and snow, just like I told you, but I had to prove it, so. And a lot of people have worked super hard in this forest here. And one of them's in here. Emily Howie has worked with folks at the Nature Conservancy and with Washington DNR out there for many days for over probably 2 years, managed to 5 years. Okay, 5 years to be managing this forest. And they're going out and they're actually marking individual trees. So this is very different than just clear cutting forests. We are going in marking individual trees and doing a gradient of forest management here. So what they were actually doing was the forest treatments were performed to represent different forest management options that we have in Washington State. So there wasn't all just clear cuts or all one type of cutting. There was different treatments. There was a range of thinning densities. They're represented by basal area factor, which is often used by forestry departments, but we often don't use those in hydrology. So this is an interesting way that we have to learn how to communicate with each other. And then there was also older, more fire-resistant species were kept, while other species such as grand fir and Douglas fir were selectively thinned. So it looks something like this. I'm going to get into it later, but it's essentially this ridge line that has a north and south aspect, and a lot of these treatment areas that we were given this map before we had any data, and we were like, look, this is where the trees were cut. And what we really want to do here is we're in this climate transition zone. So we, like I said, there's many hypotheses of what could happen here, which direction the change in forest structure pushes snowpack, but we actually get to test that for the first time. So we can ask a few questions here and directly be able to answer them. So we want to know, did the forest treatments just result in more water or less water? We want to know how it impacted the snow. And this is just first order. We're not even yet considering the different types of treatments, but which direction did these treatments push our snowpack and our water resources? And then we can actually look, because we have lots of excellent data from so many sources, we can actually look at the snowpack before and after the treatments, and we can see, okay, not just 1 year, but between 2 years before the treatments were done and after, how did the snowpack change in those areas? And then we can also say, okay, now that we answered the big questions, like which forest treatments are actually the better ones for Washington State, or which gradient of these treatments? So we can actually go into the treatments and say, okay, well, which ones of these worked, or which ones didn't work, or which are useful to us. There's two different ways we're going to do this with time. We have two different data sets. We have a time series data set that has 1 point in space, but moves over time. So we can look at the whole season. And that's how we can actually get duration. So we can know how long the snow lasted on the ground. But then we also have spatial data, which is from LiDAR data I'll talk to you guys about, which can give us 1 point in time, but over a large space. So just for fun, I'm gonna reverse this, and we're gonna go bottom to top, because I'm not gonna give you guys like the best answer to the question first, right? So we're gonna work backwards. So I'm gonna answer this last question first, and then we'll keep moving on. So we wanna go into the treatments, and we wanna see, okay, which ones resulted in snow storage? How do these treatments look? What does the snow look like in there? So we're gonna look at time series data right now. So this is our treatments. They're represented by basal area factor, which can be thought of as a gradient of thinning. And we have these points that are time series points. We have single observations of snow depth and these over this space. So we can look at some of this data, which is very fun. And I worked with John, who's here, an undergrad who worked super hard to process this data, and I'm really grateful for his effort. So on the north side of the ridge in blue and the south side of the ridge in yellow, we have a time series of snow depth at one of the plots. So, the details here aren't as important as the overview, so I'll walk you guys through it. But essentially we can increase our basal area factor, so we have the most thinned at the top, but then this is also hemispherical photography to show sky view fraction at the plots. So just gives us an idea of like, what does basal area factor mean for sky view fraction, and how do we communicate with managers? So at the top one was the most thinned, so we have the north and south sides, they both had a decent amount of snow depth here, but there was some variability, and there was differences about 2 weeks in the amount of snow storage on the north and south side of the ridge here. And in our 50 plot, which is the basal area factor 50, you can kind of see a pattern where there's a large range of snow depth ranging over at any point in time. So the range in the colored area represents the different snow depth just in one plot. And so you can see maybe up there at the very thinned areas, there wasn't as much variability, but in here, there's a lot of variability in these plots. And there's a lot of variability in just the sky view fraction. So we start to see like, okay, well, what does thinning mean for sky view fraction? And we start to think about these things. So, and at the bottom is the densest plots. You can see there's a lot of trees covering these areas, and there's less variability, but there's a lot less snow depth at both the north and south facing sides. I can summarize this. So there's a lot more plots if anybody wants to look at this time series data. But in short, the heavily thinned treatments resulted in more total snow depth and duration on north-facing slopes. And moderately thinned treatments had a lot of variability within the treatment. So it's hard to really tell which directions of pushing it in these moderate regions. But really it matters if you're just under a tree. So we know, like as hydrologists and for snow people, sky view fraction is really important. And that's not necessarily the same thing as basal area factor. So it's just important to keep in mind that maybe if you're on the really far spectrum of very thinned or very dense, you're kind of representing that. But if you're in the middle, there's a lot of variability of how much sky view fraction is available. Okay, so we can move up to question 2, because we're going backwards. So how did the snowpack change between years because of the forest treatments. So we can actually look at multiple years and look at before and after. So now we did time series data. We're going to go to the spatial data, which is our LiDAR data. I should start by explaining what LiDAR is, in case anybody doesn't know. So LiDAR, light detection and ranging. It's also known as laser scanning. You can fly a plane or a drone. You can just release a laser, you get pulses back, and then you can get distance from those pulses, essentially. So they can actually see through trees, and we can get certain models from these things. One called a digital terrain model, which is the ground surface. And then one can be a surface model. So it can actually be the surface of your canopy structure. So you can get a few things from this LiDAR data. That's essentially what I simplify this into. But we didn't just have the snow off lights, we also had snow on LiDAR. We had this before the treatments, which Jessica mentioned was flown by NCOM. So, and then we also had snow on LiDAR after the treatment. So we were super lucky that even once the forest was thinned, we got forest structure information. And that was flown by Rapid. So I do want to highlight, this is the first, this one, which was 2021, was the first snow on LiDAR over the Eastern Cascades ever. And then the second one was the second one ever. So this is like real-time data. No, but we are really lucky to have excellent collaborators that just like took a lot of their own personal time to help us with this stuff. So it's been a fun process of communicating with a lot of partners to get this data. So I hope that they're online and they can learn about what their data did for us. So we can get some things from these other models. We can get the surface. To be debated if it should be called digital terrain model or surface model, but we're going to call this a digital terrain model, which is just the snow surface, and then a digital surface model for the change in canopy structure. So you can see once it's thinned, we can know where the trees were removed. So we can essentially take these models and we can do some math, and then, which is what the math degree is for, and then we can get some information about forest structure change, which is what I want to show you guys. So we had these treatments before we had any data. This is all we thought we were going to have at the start of this project, but we were really lucky to get more. So this is those treatment areas that were estimates of where the treatments were done. And then we could just lay over forest structure. This is the forest structure pre-treatment and then post-treatment. And it's kind of hard to see with the polygons on, so we'll just like remove those. And look at our forest structure. This is pre-treatment and post-treatment. So somebody was out there and removed a lot of trees. So I'm just going to toggle back and forth because it's beautiful. Yeah, so you can see this is not necessarily what you see when you're driving on the highway and you see a big clear cut. Like really what happened here was we had clumps of trees in certain areas that we were trying to do treatments in and they were thin. So we can really see the impact of different gradients of thinning here. Okay, so now we have these two data sets. We have pre-treatment and we have post-treatment. This is canopy height models for the before and after. Once you're zoomed out, you can't see it as much. But if you do a difference map, you can really see what's going on. So this is the difference in the pre-treatment and post-treatment. And what we can do from here is define some areas. So please ask me a lot of questions about this because I'd love to talk about it. But in summary, we decided to create a binary canopy change map with the LiDAR and create treatment areas and control areas. So when I'm talking about treatment and control areas in the rest of this presentation, it's created from that distance, the difference map. Okay, well, like I said, there's not only surface models, there's the terrain models, so we can get snow depth between the years. So we have pre-treatment snow depth, post-treatment snow depth, and we have the difference between those. We learned from the time series data that aspect is super important at this site, right? So we can also get other things from this LiDAR data, such as aspect, elevation, and slope. And one important thing we do here is we classify, with aspect, we create a heat index. So we use this which this heat index is considered an indicator for the effects of temperature and topography, topographic solar radiation that controls snowmelt. So this heat index essentially, sometimes I keep saying north and south. So if you catch me, I'm actually talking about this heat index, which creates this line that you can see really clearly on the ridge of areas of low heat index and high heat index. And essentially the north side up there, it's really steep and it has the lowest heat index. And then the south side has a higher heat index. And it really splits our ridge right down the middle, essentially. And so we can actually just go ahead and split our ridge right down the middle. And we do a binary of this. And we just say, okay, areas of low versus high heat index. So for the remainder of the presentation, when I talk about that, that's the map that I'm referring to. So let's go back to our question. I just introduced a bunch of data and I need to remind you of what we're talking about. So we want to look at the snowpack change before and after treatments. So I just showed you we have all that data. Let's do something with it. Okay, we have treatment areas and control areas, and we have our high and low heat index on the bridge. And we can get snow depth from these, like I said, but it's pretty well known snow depth changes year to year. If you go skiing one year on January 1st, it's not going to be the same as January 1st the next year, right? So we can't directly compare snow depth, but what we can do is we can use the standardized depth value, and we can just say, we can normalize essentially snow depth at any point. And what we do is we say for the domain, we just say that we are only considering the control regions for those calculations because the forest structure changed. So you don't want to normalize in areas where you change the topography. So we do this standardized depth value, and it creates a map like this, which is like not fun to look at, but I had to show you anyway to prove I did it. And what we can, it's a defense. So then what we can do is we can actually look at this a different way. So the standardized depth value, we take, I previously showed over here is the difference in between the 2 years. So that's, we're taking that data and we're looking at the histograms. So let's look at those. Okay, standardized depth value, difference histograms. Let's look at pseudo data to explain what we might see. So this centered around 0 is the difference between post-treatment and pre-treatment. And what we would expect is this means that the snow depth in the 2 years was exactly the same, or like following this normally distributed histogram over 0. If it shifts over, then we would expect that it means that that's deeper after the treatments. And if it shifts this way, it means it's deeper before the treatments. So let's look at how it would look with the treatments. So we would expect, some hypotheses, is that the forest structure doesn't change in control areas. We normalized it, right? Even though the snow depth is going to change, the normalized snow depth is probably not going to change in the control areas. But since we did change the forest structure in the treatment areas, we would expect it to either move this way or that way. So we would expect some differences. And depending on which way our treatments pushed our snow depth, it will go one of these ways. So let's look at data. Okay, we have our control in the back and our histogram of the LiDAR-defined treatments in front. So you can see that there is, in fact, a shift over to the right, which means that our post-treatment snow depth is deeper in the treatment areas. Wow, we found some stuff. But if maybe that signal is not as strong as when you break it up by heat index. Like we said, heat index is really important in this location and the essentially aspects. So if we look at the high heat index areas, there's a shift of both histograms, which is a conversation that I'd love to have if anyone has any questions about that. But we mostly are highlighting the shift in the low heat index areas, which is far more dramatic. And there's different shapes in these histograms, and we can do a lot of statistics. But I think if you just look at it, you can see the difference. We can see that the snow depth is actually deeper in the treatment areas after the forest treatments in the low heat index areas far more dramatically than the south, but there's still a signal there as well. Okay. We were able to answer this question. We asked, how did the snowpack change because of the forest treatments between the 2 years? So we used the standardized depth values, and we saw that they were greater in the forest treatment areas after the treatments were done. So the forest treatments resulted in deeper snow. And the largest difference can be seen on north-facing aspects. And that's not new news, because from the first question, we saw that the low basal area factor, or the most thinned areas, resulted in the most total snow depth and duration on north-facing slopes. So the spatial and the temporal aspects are lining up here on similar conclusions. And we can get to the heart of the heart here and ask, finally, our first question last, which is, did the forest treatments result in more total water? That's what everybody wants. I was talking about details with Jessica earlier, or weeks ago, and Jessica's like, Cassie, people want to know, is this more water? Like, you need to tell us. So I am gonna tell you. So this is the treatment areas and the low heat index areas, and we can just combine these two to make it more confusing and create a few classifications to look at our data. This was the most useful to us. We have treatment areas with high and low heat index, and we have control areas with high and low heat index. And we can put all these together and look at some histograms to start. So in blue is the treatment areas with low heat index, And in orange is the treatment areas with high heat index, and the other two are corresponding for control areas. So we can see a pretty obvious shift here. In the treatment areas shifted over in snow depth, there's deeper snow in these treatment areas. This is also aligning with what we previously saw. So we can do some calculations here. We can do total area for these different definitions. We can see that the treatment areas with low heat index resulted in it was the smallest total area. So the least amount of treatments were done in these low heat index areas. And the control areas for the high heat index and the treatments are more similar. But you can see they cover different areas, but they still have pretty strong signals in their differences. So we'll take a look at that over area. Okay, so if we want to know how much water this amounts to, so we are talking about our snow depth over an area, then we can actually do some calculations and say, okay, we can say snow depth, we can create a snow water equivalent calculation with snow depth times density. We can take density measurements on the ground. Previously, I showed this little two-dimensional figure of snow depth and with the canopy structure, but realistically, it's three-dimensional, right? Like we're talking about a volume of water in a certain area. And that volume of water is usually pretty deep. So we can have some deep snowpacks here in the Pacific Northwest. And that can go down into a fairly small amount of snow water equivalent, and that depends on density. So this is the calculation we're doing to get to a volume of water in a certain area. Okay, so let's look at it. So we saw previously our total treatment areas had the smallest amount of, our treatment areas on low heat index had the smallest area, but we can see that the amount of water per area that they make up for is a lot. So it just squinting at it, it really pops out. You see that there's a lot more water per area in those treatment areas of low heat index. Interestingly, I think this is important to highlight, and I think more work can be done here, is that it's the SWE per area, so the water per area from the treatments on the high heat index slope, which I have to use it because Hannah set this up for me. So, and people online are probably, oh, they can see it. So there, so in the high heat index treatments, there's actually a little bit less snow. And, a little bit less water per area. And this is based on this calculation, and I think there could be more work done here, but I think this comes back to the idea that I mentioned of, we are managing our forests anyway. Like this is happening. And if we can manage in a way that does not hurt the snowpack or even pushes it a little bit, that's pretty good for us. So we would say overall, if we want to see, these are individual treatments on north and south aspects. But what we can do is we can look at this over the whole area, because this is just north and south individually, but what does that mean for total water over the ridge? And if you want to comprehend the volume of water over large areas, and you're in America, so my European collaborators should stop listening because they'll never want to hire me for a job after I talk about this. So, okay, a lot of times we talk about water in acre feet. Everyone's like, what is an acre foot? Okay, well, it's almost a football field. So an acre is almost a football field. And if you put 1 foot of water on an acre of space, then that's how much water an acre foot is, if you can imagine. And actually, I'm like laughing about this football thing when I was making this, but Stephen mentioned to me, this measurement was originally created for agriculture, because it's so hard to visualize the amount of volume of water. And so they were looking over their field, an acre of field, and they're like, oh, it's like about 1 foot of water over the acre. I mean, like, yeah, it can be hard to understand a volume of water over large distances. So we calculated this acre foot over our area. Well, I guess I should, yeah, that's fine. Okay, so what we did was we can say up here is the entire domain as if it was control areas only. So if we didn't change the forest structure, we use the mean snow depth from the control areas over the whole region. Then we see that there's 34.4 acre feet. So if you can imagine 34 feet of water stacked on a football field, I guess. And for the entire domain as it is, with the controls and treatments, that's how much more water we got from the treatments. And that's not expanding the treatments over the whole ridge, it's only considering the treatments as they are. So we were able to get 92.3 acre feet of water in the control and treatment areas. So, did the forest treatments result in more total water available? Yes, they did. We have a few conclusions here. The forest treatments increased total snow storage. We knew that from previous work as well, but it showed here. The forest treatments resulted in a lot more water, 92.3 acre feet of sweep over the domain compared to 34.4 acre feet without the treatment. So the treatments over this fairly small area in comparison to where they would be implemented everywhere else resulted in more than double the amount of water available. The most water really is coming from the north-facing treatment areas here. So that's just, we saw that in each one of these questions, in the time series and the spatial, no matter how we looked at it. North-facing aspects had a very clear signal. South-facing aspects, though, you know, the forest treatments on those south aspects, there was kind of like negligible effects. There's already just not a ton of snow on the south-facing aspects. So it's hard to really statistically determine, you know, where those differences, which direction they go. And I think that there could be a little bit more work done there to look at that deeper, but it's very clear signal on the north-facing aspects. And so that's really great information for us to have from this work. So when we compared within the treatments, we saw that the heavily thinned areas resulted in the most total snow depth and duration, and the moderately thinned areas had a lot of variability. So I think that, you know, we're kind of pulling this all together. And we have to think, in a management perspective, what does all of these things mean? And if we're talking about these treatments, we know that the heavily thinned areas really opened the forest canopy up, allowed more snow to be deposited, not intercepted, and we resulted in more snow depth in those areas. And the moderately thinned areas didn't have a strong signal or had a lot of variability. It really mattered if you're under a tree or not. And we know this from previous work of distance to canopy edge in other areas, in other regions, but now we have that data for this climate transition zone. Okay, if you are a forest manager and you're like listening to me and you're like, all right, what do we do with all this information? So I mentioned that forests are being managed for a lot of things, not just fire and water. We want to have healthy forests and we want to have a lot of excellent wildlife habitat, but also this takes a lot of money to manage these forests. It has to come from somewhere. A lot of times this timber is sold and it's creating some monetary income and also recreation in forests. So I'm not claiming to solve the communication between all these groups. I think this is a really much larger conversation. And I think what this work really does is just provide a little bit more information. It really bridges the gap between these two. And it says that forest thinning, especially canopy gap creation, like I mentioned, on north-facing slopes provides a viable path forward to manage forests for both fire and hydrologic resilience in this climate transition zone. So, like I said, I think that this is one piece of information that's given to this larger group that's sitting around a table making decisions. And it's essentially filling a gap of, we didn't know how forest structure was going to influence snowpack in this region. And now we have a little bit more information. And we can say, if we go open gaps on north-facing slopes, we can double our amount of water in a fairly small area. So it can be great for that. Okay, we made it. This work was not entirely my own. I think you stand up here and you're just like presenting the fun results. You're like, we doubled our amount of water. But I didn't do these forest treatments. Emily spent 5 years in the forest walking around, marking trees. I mean, like, and Susan and Jessica have been writing proposals to try to figure out to fill the data gap in this climate transition zone in Washington State. I mean, this has been a tremendous effort. And we've had people of the RAPID team here at the University of Washington who came and flew drones at our site. Really, I mean, there's like free time. Like people really like put their heart and soul into this work and to be able to give us more information. And I do want to highlight as well, like I spent a lot of time the past year in Washington State, but in my PhD, I was traveling and I met so many folks, some of them pictured here, that mentored me and they taught me how to work with hemispherical photography, what matters, like, teaching me about setting up field campaigns and trying to calculate what metrics matter in the forest. Like these people have like gave me the foundation of my education to be able to bring it back to Washington State. So I'm so grateful for all those experiences and everybody that put a lot of effort into these projects. And it's not just, I guess your friends become your work friends, become your friends in real life, because that's so true. These are like just a few people pictured. You get to like last night, I'm putting my acknowledgement slides together. Never do that at the end of your defense. You'll just like start crying. Like at the end, you're just like, you have to again tomorrow morning. You're like looking at photos of all the people you love. So if you're not pictured up here, it's like it was a hard night. So, but just know that like some of these people and all of you in this room, I mean, people at the university have taught me so much, and I'm really grateful. My team, the Mountain Hydrology Research Group, these folks have just been excellent collaborators and mentors, and sharing code and sharing methods and just hearing each other complain about whatever we need to complain about. I mean, so many folks, the taco group here also at University of Washington, you guys, so much of your code has contributed to processing this work, and I've asked a million questions and you've answered 1,000,001, so thank you. And of course, my friends and family and everyone that's fed me and cooked excellent meals with me. I'm so grateful for you all and everyone that's taken me on really awesome adventures through all this experience. And of course, my family, my closest people who have just supported me and been excellent people to bounce all of my energy and enthusiasm and tears off of. So I really appreciate all of you. And yeah, I'll just thank my committee before, and you all have been excellent mentors to me, and I look forward to our conversations and continuing this work. So. Oh. And we have like over 10 minutes for questions. We have some time.
And just for protocol, everybody in the general audience can ask questions for the next 10+ minutes, and then we will send you all the way, and then the committee will stay and ask more questions. So
awesome.
Ask them now before we send
And yeah, on Zoom, I will try to repeat the questions, and we will go to Zoom questions last if there are any questions on Zoom. Eli.
So I think that the SWE measure, was that April 1st for comparing the like acre-feet of water?
Yeah.
Was that measured April 1st?
So for this site, it's a lower elevation site. The one that we used for that, there was 2 LiDAR flights, and the post-treatment one was actually March 6th.
Okay.
So it actually was about peak snow depth for that site.
Okay, so what do you think, where like did the water go? If the water was lost or if it was gained, like where was the alternative? You know, the same snow fell all over the ridge. Like, where was the pathway to lose the water?
I'm not sure. So you're talking about the very last slides, right? Like you're talking about calculating SWE. Okay, let's just go back to that because I think I can better explain that to answer your question. If I can go back, I can't. But I have 10 minutes. So
maybe I should rephrase like in the treatment areas in the non-treatment areas that had less water at the point that you measured it. Assuming the same snow fell over the treatment and the non-treatment.
Oh, I see. Okay, sorry. Yeah.
Where would the water have gone?
I see. Yeah, I hear you. I thought you were talking about this, which I wanted to explain, but I think you're asking about physical processes. Yeah. Okay. Yeah. So the question is about the differences in physical processes in the treatment areas versus control areas, and why? What's going on? Like, what is your explanation? So I mean, this is an arid domain. I mean, we don't have like a in situ meteorological station necessarily, but it's an arid domain. There's snow interception that's happening in the control areas in the denser forests. That snow most likely it's not like on the west side where that snow is just unloading in these like large batches onto the snowpack below. It's either melting off or it's just sublimating. So we could lose our snowpack. We could lose some snow through interception that way. And then this region, it's falling into the classification of the warmer climates, and so the canopy, the tree structure is actually going to be heating up, and it could end up melting the snow as well. So I think this kind of moves into like, yeah, the next steps of this work. Like we really touch the surface of looking at snow depth over this area, but then the next piece is stream flow, really, because it's not necessarily linear, which many people in this room have studied. Is that so I think some of that water could be going to soil moisture as well. So if you have the melting, snow melting, the ground potentially not completely frozen, and it could go into soil moisture, or get sublimated back to the atmosphere. So yeah, I think any one of these processes and the next, some next work could definitely be, what is happening in those physical processes, and also how does that relate to stream flow? Does it actually equate to more stream flow? Yeah, Michelle.
Short follow-up, are there gauges in the area where you actually measure stream flow?
We put some out. Well, no, that was stream temperature. So that, I think that's definitely I haven't looked at gauges off of this immediate watershed. I know there is in the Yakima, but then off of the, maybe, I don't know if Emily knows, not in the Yakima.
No, not off the small gauge.
Not off the small, so our watershed really like splits. We go into the Teanaway, which is goes around, that's the north side, and then we go into the Clayum, which feeds the Yakima, to the Columbia. And those are pretty small, these really small tributaries that don't really get looked at a ton. I don't know of like the nearest, I was gonna assume like on lower down in the Yakima. There's a dam, like there's some dams, we have dams lower down, but not in the immediate areas of the higher elevation watershed. Okay.
Yeah, it's great talk. I was wondering what you think the transferability of this work within this climate transition zone would be for other climate transition zones or kind of other locations that might be asking the same question.
Yeah, I'm just gonna go to my
It's
last
kind of
one.
like a general question.
Yeah, I think that's a great question. I'm gonna leave it on that one. So I didn't get a chance to present on my second chapter, so I'm so glad you asked. But my second chapter that I didn't talk about here was actually looking at different elevation zones. So it was, the Clayum Ridge kind of sits at this lower, right on the band of like where houses and agriculture meet the forest, meet the snowpack, and we're studying right above that. But there are increasing higher elevation zones in the Yakima Basin watershed, for example. The NCOM data, which was aerial LiDAR, that data was pre-treatment on Clayum Ridge, but it covered two other domains at higher watersheds. And what we not higher watersheds, but higher regions in the same watershed. What we found is that we were looking at different factors such as your canopy structure, your topography, and your heat index, and how that changes with elevation, right? And we didn't have forest treatments up higher because nobody wants to go subalpine and be cutting trees, but we were able to see that the impact of forest structure as you moved up in elevation, it still mattered, but as you got higher, topography and aspect just became dominant. So it just mattered a lot of your structure, of your mountainous terrain and aspect, and so it still matters, but I think a lot of the low elevation areas are where a lot of management is happening. And so I think this would be representative of similar lower elevation areas pushed up against residential areas as well. And as you go higher up, it's going to be a smaller impact from forest management. I think interesting, since we do have a minute, is that it costs a lot of money to go out there and be cutting these trees down. I mean, it's often why there's just clear cuts, because it's hard. Like it was hard work. It took them 5 years to do something like this. So there's a lot of effort involved in these types of cuts. And I think when you go up in higher terrain, you get more complex terrain as well. Then you start to have to think about how much water benefit it would have and how much effort and money it costs to do treatments in those areas. So yeah, the lower elevation terrain that's easier to access closer to residential areas is like, that's great. But yeah, as you go higher up, I think less of an impact. Bart.
So in your introduction, you were talking about like how could be a buffer against climate change.
Yeah.
Potentially, right? So you were talking not only about volume, but also about timing, right?
Yeah.
Push that melt season out.
Absolutely.
So do you have any conclusions about that?
Oh yeah. So we had the temporal data, and I focus on two of the questions on the spatial data, but the temporal data showed so if you're looking within the treatments, there's a lot of variability for melt out within the treatments. And essentially we found that snow melts out more quickly right against trees and not as quickly in open areas. And there was differences of, I think the maximum maybe 22 days, depending on melt out, but really 2 weeks on average between even within very small areas. So if you're talking about the time, a lot of previous climate change studies on snow duration shows that maybe we're moving the snowpack 2 weeks earlier in the duration of the snow melt, but the duration for the treatments also could push it about 2 weeks in any direction. So that's duration. And then, yeah, anyway, I don't know. Did I answer your question?
Yeah.
Okay. Yeah, David was, and then George.
So, do you have a full slide picture of your snow depth difference map?
Yeah. Full slide.
Yeah, I kind of have a hard time. I saw some red areas.
Yeah. Do you want me to go to it? I can go to it.
It's exciting, right? It's beautiful.
It is. I'm so glad. Show it off. Let's do it.
And I'm just wondering if there's any relationship with the density of the treatment, like the spaces that were introduced, or did they clear underbrush away as well?
Yeah, these are great questions. You mean not just that one, but also this one?
I'm just stuck in the back of the room.
Can't see.
Did you want the forest structure or snow depth? Did you have
Snow depth difference.
snow depth difference? Let's
What
just
do you think that, like, the
presentation's
history
over.
could provide? This is great. So,
Okay, sorry.
what do you think? I mean, the red areas, the blue areas, I mean,
Yeah,
is
this
there
is
a
great.
relationship with the treatment that's
Snow
used,
depth.
with the density of the trees?
Yeah, so snow depth before and after. Okay, so there's a few pieces here. I think these are great. These are great questions. So David is asking about the snow depth in his different areas. If you couldn't tell, I just pulled it up. So first difference is that the snow depth flights are actually different times. So it's just it would have been great if they were the same day, but they capture a little bit of different forest the snow melt timing. So the first flight, so this flight actually was April 1st, and it started to capture, if I had a time series in the same plot, it started to capture ablation a little bit. So the snowpack was deeper, and it started to capture snow ablation. So what happened was the snow really melted out a lot on the south aspects, but the deeper regions on those like really hard north aspects that are super shaded, they remained fairly deep. So you end up with a map like this. Well, the post-treatment snow depth was the 6th of March. So it captured almost really well the peak snow depth. And so you didn't have ablation as much yet. There's mid-season melt on the south facing aspects, but it really captures more peak snow depth. So you have a little bit of different patterns going on because there is some ablation. So I think that adds the challenge of comparing these things. And if you look at the maps, I could overlay this with like the forest treatment areas as well. And you can see there's an increase in snow depth in certain areas, especially over here where forest treatments were done, and over here. And then on the south aspect, it's not really showing any large signal for forest treatments, partially also because there was some melt out, but just there's not a lot of snow over there. We're talking about like 50 centimeters compared to like potentially 2 meters on the north-south aspect. So I think it's a combination of all these things. And yeah, this is like the difference maps. Yeah, thanks for highlighting them because I think they're great. Obviously. George?
I usually struggle with human interventions to help solve climatic issue. I know in the beginning of your presentation you said your work is not to solve the whole climate issue and all that, right?
Right.
But I believe the reason for the climate change is not because of the presence of a lot of trees in the forest. Probably other anthropogenic stuff are causing the climate change.
Yeah.
That's leading to the snow death and the snow accumulation like loss, right?
Completely, yeah.
Do you think thinning out the trees and the forests would, of course, we are seeing present day results, doubling our snow water accumulation and all that. But thinning out the forest, do you think it will have a future climatic implication that could generate a feedback to even make our problem worse?
Yeah.
I mean, right now, so do you think it can create a few feedback in the future?
Yeah, I hear you. Yeah. The questions related to climate change and how human intervention and could cause, making these forest treatments, how they could impact in the future. How does this feel transferable in 100 years or 50 years? I mean, when we're talking about forest treatments, I think there's a few things with what you said. I agree. Climate change is not related to the forest structure. Our snow depth, temperatures are increasing. There's just differences in our snow depth. A few things. The canopy structure, unfortunately, there's we had a lot of years of fire suppression in these areas. There is already high severity wildfires that are clearing out a lot of the forest structure in these areas. And the thing is, the management is gonna happen for that. Already, we have to manage for wildfires. We have, like, it's often happening to protect homes in the lower elevation areas where, and I think like to give a scapegoat here is like the management's happening, and we are trying to say, while you're out there managing for wildfires, let's just make sure we're not hurting water resources. But I think you make a good point, is that when you're managing forests, we're talking about like 100-year scale. Like, it's not like you're in a meadow and it grows back the next year. Like, we are talking about taking down trees that maybe took 100 years or more to grow, and they're not going to come back if we have this larger feedback. So I think the short answer is there could be, and I think that that's like my point with kind of the end slide as well, is that we're kind of giving one piece of information to bridge this gap between management for wildfires and water resources, but I don't think it's like the end all solution. And I think that now you need to come into a conversation of like, okay, if we opened gaps on north slopes, how does that impact wildlife habitat? How does that impact the soil moisture content? And start and have larger conversations, like climatic larger conversations with that information. So I guess it's like the easy scientist way to be like, here's the info, I'm not claiming it. But yeah, I think that it's a piece of information that we didn't have before.
Yeah, thank you.
And it's 10:30. We're gonna let Cassie go in an hour so you can grab her at lunch.
We have one question in chat.
Okay, one question.
Okay,
in chat.
sorry, we ignored the chat. Sorry.
There's only one.
Okay. That'll be our last question.
Jeff Keck asks, nice presentation, Cassie, thanks. In terms of the impact of thinning on rain on snow driven peak flows, does your work possibly indicate that thinning on south facing slopes may have a smaller impact on peak flows than thinning on north facing slopes?
Peak flow. Okay, peak snow. He's talking about stream flow.
Like winter.
Okay, have less of an impact. Yeah, so I think for the lower elevation area, like I mentioned, there's already just not a lot of snow depth, so it's hard to look. We're talking about within like maybe 10 centimeter differences. Peak stream flow, I guess I need to reread what he said. So indicate that thinning on south-facing slopes may have a smaller impact on peak stream flow. Yeah, so I think the short answer would be that, yeah, it would have a smaller impact, but it's also respected to the amount of snow that's just available on that slope. So there's already just not a lot of snow depth. There's mid-season mill already, and there's just not a lot of snow there. While the impacts we see are a lot greater on north-facing slopes, and there's just deeper snow. So I think it would have a smaller impact, but it's also, if you were to scale it to like to how much snow there already is, that would be interesting for peaks stream flow. Yeah. Sweet.
Right. So let's-